Good morning, my dear students. This is Sir Mike. Today we're going to discuss Module 6 and it's on the process of finding the derivatives of trigonometric functions. Let's start with the conversion of degrees to radians. So, in converting degrees to radians, anyway, this is just a recall, no? So, if the given is expressed in terms of degrees, the given angle is expressed in terms of degrees, and you want it to convert it to radians. So, the formula is you just multiply the angle in degrees by pi all over 180 degrees. So, for example, you have 30 degrees, you need to multiply 30 degrees by pi all over 180 degrees to get the radian equivalent of 30 degrees, which is pi all over 6. Now, on the other hand, if you want to convert radians to degrees, okay, the given here is the angle in radians. You need to multiply the angle in radians by 180 degrees all over pi. So, for example, if the given angle is pi all over 3 radians, you just multiply pi over 3 by 180 degrees all over pi to get the degree equivalent of pi over 3. So, the answer is here is 60 degrees. Okay, so here we will be looking into the special angles, okay, expressed in degrees and the equivalent of these special angles in radians. So we will be looking into the process of converting degrees, special angles, converting degrees to radians, and vice versa using the unit circle. So when we speak of a unit circle, the radius is equal to 1. So you can see here that the unit circle is divided into several parts. So we have here 0 degree, and then 30 degrees, 60 degrees, 90 degrees, 120 degrees, and so on and so forth. And if you want to look at the degree measure of a semicircle, that's 180 degrees. Now let's start with the basic. So 0 degrees definitely or 360 degrees is equal to 2 pi. Okay? And 180 degrees, the equivalent of 180 degrees in radians is pi. So we'll be using this relationship or this conversion factor in order for us to look at the equivalent, the radian equivalent of this uh, angles which are measured in terms of degrees. So since 180 degrees is expressed in terms of can be expressed in terms of radians and the radian equivalent of that is pi, definitely if we want to divide this semicircle into 6 parts, one part is 30 degrees. So since 180 degrees is equal to pi, the equivalent of 30 degrees therefore in radians is pi all over 6 because that is one part of the entire semicircle. So that is pi all over 6. And correspondingly, the equivalent of 60 degrees is 2 pi all over 6 because we are getting here 2 parts of out of 6. Okay? 2 parts out of 6. So if we reduce that, the radian equivalent of 60 degrees is pi all over 6. Now, you look at 90 degrees. Since 180 degrees is pi, we just simply divide pi by 2 because 180 divided by 2 is 90 degrees. Therefore, the radian equivalent of 90 degrees is pi all over 2. And you look at 120 degrees. That is 4 parts out of 6. Okay, so 4 parts out of 6. So if we want to reduce that to its lowest terms, your 4 pi over 6 is 2 pi over 3, which is the radian equivalent of 120 degrees. And even 150 degrees, we are actually looking here at the 5 parts, okay, 5 parts out of 6, okay, so 5 parts out of 6 or 5 pi all over 6, that will be the radian equivalent of 150 degrees. Well, of course, 180 is equal to pi. 180 degrees is equal to pi. You look at 210. Okay, we want to add 130 degrees to 180. So meaning to say, we are adding 1 over 6 pi to pi. So therefore, your 210 degrees is equal to 7 pi all over 6. Okay, and here you follow the same process for 240 degrees. So uh, you're going to add here 60 degrees to 180 to get 240. So meaning to say, you are adding pi all over 3 to pi. So the equivalent of that is 4 pi all over 3. So you can actually solve the equivalent of the remaining degree measures using that process. Okay, so just bear in mind that 180 degrees is equal to pi, and here, okay, in the beginning we divided the semicircle into 6 parts. So uh, and please remember that for 30 degrees, the equivalent of that is the equivalent of 30 degrees in radians is pi all over 6. Okay, now let's try to look at the different trigonometric function values. So you will be needing these trigonometric function values if you will be solving later on specific problems on derivatives of trigonometric functions. Anyway, this is just a recall. I know that these trigonometric function values were introduced to you when you were still in grade 9. So let's try to look at the different trigonometric function values. And there are only several numbers that you need to memorize in order for you to look or to solve the trigonometric function values of the different special angles in a unit circle. We are considering here a unit circle because the radius here is 1. The radius of the circle is 1. Now, let's try to look at the trigonometric function value of 30 degrees. The equivalent of 30 degrees, you're aware that the equivalent of 30 degrees is pi all over 6. So your sine or your cosine, the first coordinate refers to the cosine value, and the second coordinate is actually the value for sine. So here, if you want to solve cosine of 30 degrees or cosine of pi all over 6, that is equal to square root of 3 all over 2. And sine of 30 degrees is 1 half. Okay? So if you look at the values that are present in this illustration, you can see that there are only several values that you need to memorize. You have 1, 0, square root of 3 all over 2, and 1 half. Okay? Now, you look at 45 degrees. Okay? You look at 45 degrees. So, when you want to get cosine of 45 degrees, that will definitely give you square root of 2 all over 2. Okay, and the sine value is the same with uh, the cosine value. So if the cosine value of 45 degrees is square root of 2 over 2, the sine value of 45 degrees is square root of 2 all over 2 also. Okay, and then you look at the cosine value of 60 degrees. Cosine of 60 degrees will give you 1 half, and the sine of 60 degrees will give you square root of 3 all over 2. Now, it's easy for you to memorize these trigonometric function values by simply visualizing the location of the point. So for example, here in the cosine of 30 degrees, you just draw a vertical line, okay, along the x-axis, and you will notice that the value along the x-axis is greater than 1/2. And you are aware that the square root of 3 all over is greater than 1/2. It's approximately equal to 0.776 something. Okay, and then if you want to draw a horizontal line, okay, joining this point and the y-axis, you will notice that the function, or the value is 1/2, okay, along the y-axis, and that is actually equal to the sine value of the degree. Sine 30 is equal to 1/2. Okay, then the remaining trigonometric function values will only differ in terms of the sign. So for example, if you want to look at cosine 120 degrees, that will give you negative 1/2. Well, definitely, if you draw a vertical line along the x-axis, you will notice that the value will fall at negative 1/2. And if you draw a horizontal line, okay, joining the point and the y-axis, you will notice that the value will be approximately equal to square root of 3 all over 2. Okay, and since your 3 pi all over 4, or 135 degrees, is located in the second quadrant, you will notice that the function values are negative square root of 2 all over 2, cosine of 135 is negative square root of 2 all over 2, and sine of 135 degrees is square root of 2 all over 2. The only difference is of course the sign. If you want to compare the trigonometric function values of 135 degrees and your 45 degrees, so you notice that the sign of the first coordinate are different, okay, or will differ rather. Okay, so you look at 150 degrees. The cosine of 150 degrees is negative square root of 3 all over 2, and it's quite similar to the cosine of 30 degrees in the first quadrant, but the only difference is the sign. So it's negative square root of 3 all over 2 and 1/2. And since this is a unit circle, cosine of 180 degrees is negative 1, and sine of 180 degrees is 0. Okay, and then you look at the third quadrant. Actually, the values, the trigonometric function values, are just mirror images of the first quadrant. The only difference is, of course, the signs. It depends on the location of the angle. Okay, so you look at the fourth quadrant. We have here 330 degrees, 330 degrees, and cosine of 330 degrees is square root of 3 all over 2, and the sine of 330 degrees is negative 1/2, and it's similar to the sine of 30 degrees. That is 1/2. The only difference is the sign. Okay, so the angle located below the x-axis is the sine value of 330 is negative 1/2. Okay, and you can actually look also at the trigonometric function values of the remaining angles here in the unit circle. Okay, so there's a need for you, again, I would like to repeat that there's a need for you to memorize all these trigonometric function values, because you will be needing these trigonometric function values in solving some problems on derivatives of trigonometric functions. Okay, so let's proceed to the derivatives of trigonometric functions. So let's start with the basic trigonometric functions. Y is equal to sine x, and y is equal to cosine x. And the derivative of y is equal to sine x is cosine x. Y prime is equal to cosine x. And the derivative of cosine x is negative sine x. Now, using these basic derivatives, we can actually derive the derivatives of the remaining trigonometric functions. You're aware that the derivative of y is equal to sine x is y prime is equal to cosine x. And the derivative of the function y is equal to cosine x is negative sine x. And as I said a while ago, you can actually derive the remaining derivatives of trigonometric functions using these first two derivatives of trigonometric functions. So let's look at the derivative of y is equal to tangent x. And you're aware that y is equal to tangent x can be expressed in terms of sine x and cosine x. That is, y is equal to sine x all over cosine x. And here, you can apply the quotient rule. So the quotient rule is v du minus u dv all over v squared. So here, the derivative therefore is equal to cosine x times the derivative of the numerator sine x, that is cosine x, minus sine x times the derivative of the denominator, that is negative sine x. And that is all over the square of the denominator, which is cosine x. So that will give you cosine x squared. Okay, and then simplifying further, we have here your cosine squared x, because your cosine x times cosine x is the square of cosine x, plus sine x, negative sine x times negative sine x, that will give you sine x squared. Okay, and this is all over cosine x squared. But you're aware of the Pythagorean identity. That is, if we have your cosine squared x plus sine squared x, that is equal to 1. So definitely you can replace the numerator by 1. So the derivative therefore is equal to 1 over the square of cosine x, which is simply equal to the square of secant x. Now let's look at the derivative of the function y is equal to cotangent x. You can actually express your cotangent x in terms of sine and cosine. So here you can see that your cotangent x is equal to cosine x over sine x. And again, you need to apply the quotient rule. So sine x v du, sine x times the derivative of cosine x, that is negative sine x, minus cosine x times the derivative of sine x is cosine x all over sine x squared. Then simplifying further, we now have negative sine squared x, or sine x squared minus cosine x squared all over sine x squared. Okay, and if you try to look at the simplified form, you have you can factor out negative 1. So negative 1 times the quantity of sine x squared plus cosine x squared all over sine x squared. And definitely the numerator, okay, your sine x squared plus cosine x squared can be replaced with 1, because that's a Pythagorean identity. So you'll be having negative 1 all over sine x squared. Therefore, the derivative of the function y is equal to cotangent x is negative cosecant x squared. Okay, then you can apply also the same process for finding the derivative of cosecant x. You use again the quotient rule. So applying the quotient rule here, anyway, you are aware that your cosecant x is equal to 1 over sine x. You apply the quotient rule, you'll be able to get the derivative, which is negative cosecant x times cotangent x. And even for the function y is equal to secant x, you're aware that your secant x is equal to 1 over cosine x. If you apply the quotient rule, you have cosine x times the derivative of 1, that is 0, minus 1 times, of course, the derivative of the denominator, which is negative sine x. So simplifying further, you have sine x over cosine x squared. But your sine x over cosine x can be expressed in terms of tangent x, and there's cosine x that is left in the denominator, which is equal to secant x. So the derivative therefore is tangent x, okay, times secant x. That's the derivative of secant x. Now, if we have the function expressed in terms of a function of x, the trigonometric function uh, is expressed in terms of a function of x, which is actually u. Okay, we'll be using u, the arbitrary variable u. So the rules will further lead us. It says here that the rules will further lead us to the following derivatives. So if you want to take the trigonometric derivative of a function containing u, and it is being specified here that you use a function of x, then you will have the following derivatives. So y is equal to sine u, then your y prime is cosine u du. If y is equal to cosine u, your y prime is negative sine u du. If y is equal to tangent of u, your y prime is equal to secant u squared times du. If y is equal to cosecant u, your y prime is negative cosecant u cotangent u du. And if y is equal to secant u, your y prime is tangent of u secant u du. And lastly, if y is equal to cotangent u, your y prime is equal to negative cosecant u squared times du. Okay, now we will be looking into some of the applications of derivatives of trigonometric functions. So here we will be solving two word problems on the application of derivatives of trigonometric functions. Okay, and you're aware that we were able to discuss already 5 applications of derivatives of functions. So since we are done with the discussion of the derivatives of trigonometric functions, we're going to apply these derivatives of trigonometric functions in solving word problems on trigonometric functions. So this is the first problem. No? You are asked to find the equation of line tangent to the graph of f of x is equal to cotangent x at x is equal to pi all over 4. So just like the usual thing that we usually do in finding the equation of a line tangent to a curve, we need to follow several steps. So the first thing that you need to do is to get the point of tangency. Okay, you need to get the point of tangency. Then you need to solve the slope of the tangent line, and of course you apply the point slope form of a line to solve for the equation of the tangent line. Now, bear in mind that if you are evaluating trigonometric functions, be sure that you set your calculators in region mode, because your calculator will give you a different answer if that is being set to the degree mode, which is the default. Okay, so let's try to look at the process of finding the point of tangency. Just simply substitute the value of x to the original function. The original function is y is equal to cotangent x. Your cotangent x is actually 1 over tangent x. Okay, if you cannot find that in your calculator, you can simply get the reciprocal of tangent x, that is equal to cotangent x. So if y is equal to cotangent x and your x is equal to pi all over 4, your cotangent of pi all over 4 is equal to 1. Therefore, the point of tangency is pi over 4 and 1. Again, may I remind you to set your calculator to the region mode, because your calculator will give you a different answer if your calculator is set to the degree mode. Now let's proceed to the second step. So this here we will be looking at the slope of the tangent line, and you're aware that the slope of the tangent line can be solved by getting the derivative of the function, and then replacing x by the desired value. So here, the function is cotangent x, and the derivative of that, and we were able to derive the derivative of cotangent x while ago. That is negative cosecant cosecant x squared. Then your cosecant is equal to the reciprocal of sine x. So your y prime here is negative 1 over sine x squared. So replacing the value, or replacing x by pi all over 4, you have negative 1 all over sine of pi over 4 squared, and you will be able to get a value of negative 2. So that's the slope of the tangent line already. And now we apply the slope of the tangent line and the point of tangency. We use the slope of the tangent line and the point of tangency in getting the equation of the tangent line. Okay, so you are aware that the point slope form of a line is y minus y sum 1 is equal to m times the quantity of x minus x sum 1. So here you have y minus 1 is equal to negative 2 times the quantity of x minus pi all over 4. So your y sub 1 is negative 1, your x sub 1 is pi all over 4. And then your slope, of course, is negative 2. So you have y minus 1 is equal to negative 2x plus pi all over 2. So y therefore is equal to negative 2x plus pi all over 2, because if you multiply negative 2 by pi all over 4, that will give you positive negative 2 times negative pi all over 4 is positive pi all over 2. So you have here pi all over 2, and then you transpose your negative 1 to the other side of the equation. So the equation of the tangent line therefore is y is equal to negative 2x plus pi all over 2 plus 1. Okay, now we're going to look into the application of the derivatives of trigonometric functions in the field of physics and information and technology. Okay, and nowadays we can actually program a machine to create a particular object, and you can actually, there are cases wherein they are already printing three-dimensional objects using computers. Okay, so for example, it says here, okay, a machine is programmed to move an etching tool such that the position of the tool is given by these functions. You have x is equal to 2 cosine of 3t and y is equal to cosine of 2t, where the dimensions are in centimeters and time is in seconds. So you need to find the velocity of the tool for t is equal to 4.1 seconds. So we will be using the second set of derivatives of trigonometric functions here. So because here in this particular problem, in the given problem, the trigonometric derivative contains a function containing u. Okay, so the derivative of a function contains u, which is a function of x. So anyway, the given problem, okay, so the given problem has two functions. We have the movement or the distance function in the horizontal axis and the distance function in the vertical axis. So you have your cosine, you have your x is equal to 2 cosine of 3t and y is equal to cosine of 2t. So we need to get the vertical or the velocity of the object along the horizontal axis. So that is of course dx all over dt. So the function we'll be using here is x is equal to 2 cosine of 3t. And you're aware that if we get the velocity of the moving object, or the tool rather, in this particular problem, you just need to get the derivative with respect to time t. So dx all over dt is equal to negative 6 sine of 3t. So your vx therefore is equal to, okay, negative 6. The derivative of the function 2 cosine of 3t is negative 6 sine of 3t. So you apply the second set of formulas for the derivative of trigonometric functions. So the velocity therefore of the tool along the horizontal axis is solved by substituting 4.1 to the derivative. So negative 6 times the quantity of sine 3t. So 3 times 4.1. That will give you, if you enter this in your calculator, 6 times sine of 3 times the quantity of 4.1, that will give you 1.58 centimeters per second. Okay, so that's the velocity of the tool along the horizontal axis. Now if we want to find the velocity of the tool along the the vertical axis, okay, the vertical axis, you have y is equal to cosine of 2x. This is along the horizontal axis, the one that we solved a while ago, that is along the horizontal axis. Okay, so along the vertical axis, y is equal to cosine 2t. So y prime is equal to negative 2 sine of 2t. That's the derivative. And the derivative is actually the velocity of the object along the vertical axis. So you have negative 2 sine of 2 times 4.1, that will give you negative 1.88 centimeter squared. Okay, so in physics, you are actually solving for the resultant vector. And if we speak of the resultant vector, we need to get the magnitude of the vector, and of course the direction. Okay, so here we are only aware of the velocity of the tool along the horizontal axis and the vertical axis. So there's a need for us to solve the magnitude of the vector, or the velocity in total of the moving tool. So the velocity can be computed using this. Okay, you encounter this in the component method of finding the resultant vector. So the magnitude is solved by the formula v is equal to the square root of vx raised to the second power plus vy raised to the second power. And you are aware of the velocity of the object along the horizontal axis, that's 1.58 raised to the second power, and the velocity of the object along the vertical axis is negative 1.88 centimeter per second raised to the second power. Okay, and if you enter that in your calculator, you will arrive at the magnitude of the resultant vector, that's 2.46 centimeters per second. Now we are not yet done, because we need to find the direction or the angle. Okay, so the direction of the moving object or the moving tool can be solved using tangent theta is equal to, of course, the velocity along the vertical axis all over the velocity of the tool along the horizontal axis, vy over v sub x. Okay, v sub y all over v sub x. So your theta therefore is equal to tangent inverse of the velocity along the vertical axis, that's negative 1.88, that's over 1.58. So that will give you negative 55.51 degrees. Okay, so that will give you negative 55.51 degrees. And if you try to look at the velocities of the moving object, okay, it's directed to the fourth quadrant, because your v sub y is negative and your v sub x is positive. So therefore it is directed towards south of east. Okay, south of east, if we are referring to the Cartesian plane. Okay, so here the tool moves, we can conclude that the tool moves with velocity of 2.46 centimeters per second. That's the magnitude of the resultant vector. okay, 55.51 degrees south of east. Okay, so those are some of the applications of the derivatives of trigonometric functions.